Welcome back to Futureland, your friendly and most reliable source of tech news, the latest gadgets, and anything related to the tech world. The technology used by SpaceX nuclear rockets could revolutionize space travel. How does it function? It might reduce travel times to remote places, increase launch flexibility, and increase astronaut safety while in space. Today, we will explore how Elon Musk's new nuclear rockets are shocking the entire space industry. When there is energy, there is life. Therefore, even in the vacuum of space or on a planet far beyond Earth, the use of nuclear energy and a dependable, sufficient supply of energy does have the capability to accelerate, enable, and reduce the expense of our outer space flight. As NASA continues its project to build a manned moon colony from a goal to a potential human visit on Mars, a fascinating integration of technology, financing, and political ambition is on the brink of creating space-borne nuclear reactors. The White House gave NASA a 10-year deadline in 2020 to produce a 10-kilowatt nuclear power plant on the surface of the moon. At this time, this plan is the company's primary goal according to the Space Technology Mission Directorate, or STMD. Congress also allocated $110 million in July 2021 for NASA, even without the agency's request for funds, to advance the development of a new nuclear spacecraft that can carry cargo and passengers to distant planets. The space agency's stated goal of building a lunar colony by 2030, which is difficult, if not impossible, to achieve without nuclear power, much less even landing people on Mars, is a probable reason for this enhanced degree of priority. Luckily, no significant scientific advancements are required for the creation of a nuclear reactor for use in interplanetary travel. In fact, the US Air Force created and launched a working version in 1965, marking the only time the US so far has attempted such. The difficulty lies in navigating the complex system of laws that regulate all things nuclear, ensuring that any method chosen for using nuclear energy in or around Earth will not unreasonably limit NASA to just the moon's surface or any other restricted outer space location. In a perfect scenario, crewed missions to the moon and Mars could be accomplished using the power of the atom. Visualize opening the lip or hole of an inflated balloon to better understand thrust, which involves rocket propulsion. The balloon is thrust in the reverse way when the opening lets air out. In order to generate thrust by forcing gas out of the engine's nozzle, most propulsion systems combust a combination of fuel and oxidizer, like liquid hydrogen and liquid oxygen respectively. The rocket is subsequently launched in the desired direction. However, there are different options available than chemical propulsion systems. Nuclear thermal propulsion systems have twice the efficiency and power of chemical rocket systems. Since the 1950s, NASA has been researching NTP systems, which use nuclear fission to produce the temperature needed to convert liquid fuel into gas and provide thrust. These systems have significant benefits for spaceflight, even if in the coming years that spaceships will be launched from the surface of the Earth by chemical rockets. NTP systems can create 2 times as much thrust as chemical rocket engines while utilizing nearly identical quantities of fuel, making them more powerful and effective by a factor of 2. Experts forecast that the risk to humans, including cosmic radiation, microgravity, and boredom, would be lessened by cutting the duration required for a rocket to reach Mars by up to 25% or around 2 months. NTP engines would provide missions to Mars with more flexibility. Because of the weight of the fuel, the time frame for a manned space chemical rocket journey to Mars is only available once every 2 years and 2 months, whenever both planets' orbits are properly aligned. Given the effectiveness of an NTP system, getting to Mars could only take far less fuel than using a chemical rocket and uranium that is just slightly larger than a pebble. The strong engine would enable flights to actually happen even when both planets are not in their optimal locations, so it would lessen the 2-year period when travel is possible. With nuclear propulsion, there would be more possibilities for manned space travel and fewer trips needed to bring fuel for this type of trip into interplanetary space. Those fuel needs are substantial. The precisely built 420-ton International Space Station took well over 30 launches over such 10 years to complete. A chemical propulsion system needed for a round trip to Mars would involve launching between 2 to 10 times as much tonnage from Earth, which would be quite expensive. Consider the fact that the Orbit Launch System, or SLS, the most potent rocket NASA has ever created, has yet to launch and is only intended to carry 95 metric tons to space at a cost of $2 billion for each liftoff. In the event that the SLS is replaced by more efficient and reasonably priced rockets, like SpaceX progressing in fully reusable Starship, the single launch tonnage limit would increase to over 100 metric tons, and the expense per launch should decrease. In addition to facilitating human travel, setting up settlements on Mars, producing an interplanetary society, and saving mankind from extinction, the 120-meter tall Starship has the potential to profoundly revolutionize how space scientists go about their work. They might deliver larger and heavier equipment more regularly and significantly less expensively if SpaceX projections of cargo launch costs as low as $10 per kilogram is offered. On Mars, rovers can be dispatched collectively as opposed to alone. There may be a rise in satellite fleets in low Earth orbit and the development of space telescopes. It is possible that satellites, space sciences, and astronomy will all make important advancements. By employing retro rockets and steerable wings to lead the first stage to a landing after it re-enters the atmosphere, the 70-meter tall Falcon 9 has already revolutionized the aerospace industry. With such a spacecraft, SpaceX established recyclability. More than 50 of such rocket launches are expected from the company this year, which equates to almost approximately one launch per 7 days. SpaceX is likely to price $67 million on a Falcon 9 launching. That is a lot less than its competitors. Besides that, it has a fast launch frequency and effective reuse. But Elon Musk was still not satisfied. In 2016, at an IAC in Mexico, he drew blueprints for a rocket that would visit Mars. Eventually, the rocket is then referred to as BFR, short for Big Falcon Rocket. Starships was created from the original concept, but the focus on cost and reusability was maintained, making launches dull and repetitive. Stainless steel, which is heavier than the aluminum alloys used in the majority of spacecraft, serves as the rocket's body. The 33 Raptor engines cramped onto the back of SpaceX Super Heavy booster burn methane instead of traditional kerosene-based rocket fuels. In addition, being considerably cheaper, it could also be made on Mars by water and carbon dioxide combinations. The launcher will go for 6 minutes and then return to the launch pad, where it will spend an hour being resupplied and made ready for another launch, according to the manufacturer. Starships can also be recycled. A tanker version of the vehicle could refuel a carrier Starship once it was in orbit, enabling it to deliver 100 tons of cargo to the Moon or Mars. Each spacecraft is capable to be launched 3 times every day. On a larger scale, nuclear thermal propulsion would resemble a boat, a more compact nuclear-powered rocket that could also dock with certain other shuttle connectors in orbit prior to actually launching its own cargo alone. This arrangement works similarly to a chemical propulsion system because the combustion chamber is changed with a nuclear reactor that combusts a cryogenic propellant and blasts through the nozzle to generate thrust. The procedure almost identically displays a rocket engine in flames from the outsider's perspective. The primary issue with nuclear thermal propulsion is the high-performance reactor it employs, which can run at temperatures as high as 2,500 degrees Celsius, which is alarming for passengers and material engineers. The reactor would also require massive quantities of cryogenic propellant, which will likely come from on-orbit storage tanks and hence bring their own special technical challenges. The method's laser-like focus does have a benefit. You work quickly because the propulsion system simply requires to be operational for a short time. After then, the spacecraft would have all the speed required to reach Mars or return to Earth. Because of its simplicity of design, nuclear thermal propulsion is a preferred method for a Mars mission. The NASA-sponsored National Academy determined that this approach was the most likely to lead a crew voyage to Mars in 2039, and congressional appropriators gave it a $110 billion raise in July 2021. A fusion-powered spacecraft potentially can be used to ferry people to Mars after other technologies are developed. Viewing Mars and the stars more clearly in the 2050s could be as normal as getting a plane ticket at the moment. In the future, it may as well be as simple as visiting planets in our solar system. So what do you think about the possibility of actually going to Mars? Leave your thoughts at the comment section down below. Also, don't forget to hit the like button, subscribe, and turn on the notification bell to be notified whenever we have a new upload. Again, this is Futureland, and thank you for watching. We'll see you in our next video.